Alright, so let's work out what this pretty good measurement looks like on a simple example. So here's an encoding. It's an encoding of strings x that take 2 bits, so there's 4 possible x's and that's a possible arbitrary encoding. And our goal is, given one of these states, ho x, identify the string x by making the best measurement possible. We don't really have any clue, so what we do is that we resort to our second best option, which is use the pretty good measurement. How do we compute the pretty good measurement operators? First of all, we have to compute the average density matrix of the ensemble, which is just summing over all possible x. So I can compute rho, which would be the sum over all possible x of rho x, which will be, so if you sum the first two here, you see that you get a quarter times the identity matrix plus, and if you sum the other two, there, you get again a quarter times the identity matrix, so I get a half times the identity matrix. These are single qubit states, so I can verify that the trace of rho is 1, it's a density matrix. Good. Now remember the definition of the measurement operators for the pretty good measurement. I need to define mx to be equal to rho minus a half times rho x times rho minus a half. So here what do we get? Let me compute here rho minus a half. It's simply going to be equal to root 2 times the identity. So the conjugating by rho minus a half will simply multiply the states by a factor 2, which means that we get m00 will be equal to twice rho 00. So it's a half the projection on 0. Then I can write m01. This will be a half 1 projection on 1. m10 is a half the projection on plus, and m11 is a half the projection on minus. That's my measurement operators. Again, you can check that they're positive semi-definite and they sum to identity, so it's a valid P of M. It'll always be the case because it's a PGM. Now let's compute the success probability. By definition, this is equal to the sum over all x of the trace of mx times rho x. And what do I get? Well, for instance, m00 times rho 00, then I just get 1 times the normalization factors, which is 1/8. So each of the 4 terms is equal to 1/8, 1/8, 1/8, 1/8, and so we get a half overall. And as we saw in the previous module, the success probability of the PGM, we can use this in order to get a lower bound on the min entropy of the ensemble of states. So as a consequence, we get that the min entropy of x conditioned on E, given the family of states that are described here, will be at least half the minus log of the success probability of the PGM, of the pretty good measurement, which will give me at least half minus log of a half, which is 1, so I get at least a half. This is a lower bound on the min entropy. What you can check if you do the calculation is that on this example, the min entropy of x given E is equal to 1. This is not too hard to verify. And so you see that, as promised, it's within a factor half of the optimum. Actually, it's exactly a half of the true answer, meaning that this is sort of a bad case for the pretty good measurement. It's doing as bad as it could ever do, which is not so bad. It's a factor half from the optimum, and it's a reasonable measurement to be using in practice. It's also going to prove a very powerful tool in theoretical analysis.